You can thank those other people.
Okay. Thank you, everyone. Actually, this is a for student, by students event. What we hope is through this kind of presentation, students actually have their ownership of their math learning. It's not anymore like this is from the textbook, this is from my teacher. No, this is from you, your own discovery. And you connect math to your daily life. Everything that you see, everything that you feel, you touch, all has something to do with math. Am I correct? Yeah. Especially this. This is iPad mini. We are going to give this out as the, I think the winner for the Raffle tickets. Has a lot to do with math, right? I want to thank all of you. Many of the faculty members, actually, I'm not the only one. This starts with a lot of clubs. We have TASA Club, Pi Club, CS Club, iCreator. We have Buddhist Club, and also many faculty members. They are all here. Can I have those of you who have involved, like from CS and our dean, yeah, and all those club people, yeah, all the teachers, come here. Let's come over here, yeah. Let's give them a applause. Charlie. And we have support from the science, so we also have support from the STEM, so we have director from the STEM, and also we have dean from art. Can we all have you come over here? And Davis, okay, Dr. Davis, would you please come over as well? And there's a hero behind this is Charles Jones. Well, I don't know where is he. Charles, yeah.
He's a very humble man. Charles is one of our best employees, and he's a guy that we can turn to facilitate, and I'm going to thank you on his behalf because clearly he's in hiding now, so thanks.
Yes. Anyway, Ellen, where's Jason? Yeah. All those presidents of the clubs, Hillary, come out here. I mean, they have worked tirelessly, you know, not just us. Where would you come here? Yeah. Where's Hillary? Where's Jason? Yeah. Come over. Yeah. We have a lot of support from many, many students, okay? They take this as what they want. They want to share, you know, all these good thoughts with all of you. And we are hoping after this, excite you the feeling about learning math, right? And also, you know, we want to celebrate the victory of your learning, okay? Thank you very much. And we are going to start our drawing now. Okay, thank you everyone. We are going to have our, yeah. The first winner.
Am I going to read the whole number? 388804. What's that? Oh, she doesn't have her side?
No, she has the name right on the.
Okay. Good. Helena? Helena? It's like the first day of class. One, I don't know, 388907.
So that's a second winner. Yeah, okay. This is a high school student.
Oh, high school student. 388307.
Oh, good.
Hey, we have a winner. 38866. How's that? 38866.
Josie Wang.
388.
Joyce Wang.
Joyce Wong?
Joyce Wang.
388439.
Jesus Lopez.
Want me to read the names as well? Oh, okay. Oh, I can see their names. 388283.
Yeah, Jesus Lopez. That's you? Oh, congratulations.
Okay, this last one was 388283. Jeff. I can't read the last name. I know, it's difficult to read. 388266. CQ Lu.
CQ Lu. I think it's my student. They did a great job for me.
One more. 388749. 388749. Joyce Wong. She must have bought several.
Now we are going to have a word for this.
Which phone? iPhone.
388641. Fernando B. What's next? Oh, another one. Okay. Three 38899. 388899. 3888899. Full house. Oh. Yeah, good luck. Can't read the name. Another one?
Now is, what is it?
For whatever this is, 388563. It's yours. One I can read. Arlen De La Rocha? Or Arian De La Rocha?
Oh, your student? Oh, okay. Would you like to represent your student?
It's a hat box. It's a hat. And we have another box? Another one of those? 388582. Kevin. I can read that. Kevin. Last name I can't read.
Kevin Sandy.
Yeah.
Sandy Harpo.
388582. I can read the numbers. 388582. That's somewhere in pi, right? Did we learn that today? That number is somewhere in the string of pi. Somewhere, right? Right. Yeah, you can find it for me. Great. What's next? Oh, this is what's the... Are we going to do all those pens? No. Let's not do all those pens. No. No. If you want to draw them out later, do that. Okay, grand prize. Now you're gonna check your ticket stubs, right? Now you'll check. Do we have a drum roll? There we go. If you guess the number, no. 388 373. 388 373. What's your name, John? Here it is. John, right?
Yeah, John.
John, what's your last name, John?
Win.
He's right. He wins. So John wins. No. Oh, hey. Okay. Ready?
Next year.
Right. Yeah. You want me to say that? I'm supposed to tell you we'll contact the people that we drew their numbers. I know. We're not going to keep drawing till, the end of the night. Okay, you didn't come here to listen to me draw numbers. Again, we have another distinguished guest from Caltech. It's nice that we've had that relationship over the years. There's several relationships here. Caltech and Dr. Ho from Caltech, Applied Mathematics and Computational Mathematics, is here to tell us about how mathematics improves the quality of our life, which, just the air conditioning, the lights, and just about everything that we enjoy creature comfort-wise is mathematically based. But he's going to give you a lot more interesting things than that. He's a professor of applied mathematics and computational mathematics, the Charles Lee Powell professor. So, Dr. Ho, welcome.
Good afternoon, everyone. I'm very pleased to be here today to participate and celebrate the Pi Day with all of you. I'm very impressed the room is packed. I thought that if only very few people would show up, I would do it anyway. But there's several messages I would like to convey today. So first of all, for many of you, maybe you would think that the mathematics is hard, right? Maybe something that whenever I travel on the airplane somewhere, people ask me, what do you do? I say, I'm a professor in mathematics. Almost 90% of people say, oh, mathematics is a subject I hate. I'm not doing well, So I guess many of you may share the feeling. But today I want to tell you, actually, if you learn mathematics well, although there was a steep learning curve, but it will pay off very well. So if you are going to illustrate through many, many examples, that if you master mathematics to some level, you really have an edge over other people in your career, in your life. You can be rich and famous, and a lot of interesting things could happen because you know mathematics, okay? And also the second purpose, as Charles mentioned, that your neighbor, somebody from Caltech, I want to convey that we also a friendly, normal human being, not somebody like you see on the Big Bang Theory, So you can actually behave just like a friend in your neighbor. So we're really a neighbor, right? So, and also today I would like to, this is the first time I give this kind of talk, that I'm trying to give this kind of public lecture. So I was a little bit nervous because when Yu Chan told me that she organized this big event, I said, well, I can recommend you a number of outstanding speakers. Unfortunately, many of them are too busy today, and she cannot get them to agree to come today. I said, well, I could be your backup, okay? Unfortunately, she needs my backup. So when I need to make the decision, I need to contact some people who really a good speaker. So these are the two gentlemen that I would like to thank, in particular, Professor Tony Chan. Professor Tony Chan used to be the professor at UCLA. She was one of the co-thesis advisor of Yu Chang Chan. He was department chair and dean of UCLA, and then become the deputy director of National Science Foundation before he took up the presidentship in Hong Kong University of Science and Technology in 2009. So he has given a number of very outstanding public lectures. He was very generous to share some of his slides with me. And also Professor Zhou Wei-Shen from National University of Singapore. And he also was generous enough to let me use some of his slides and plus some of my own preparation. So let me start with this slide. So it is an old slide. It is a photograph from Los Angeles Times almost 15 years ago. I think it's very appropriate for this audience, right? Because it says, look at the title, mathematics equal to fear, right? For two-year college. I think PCC is like a two-year college. Why is it a fear? Because for many students, this subject it is a nemesis that will block them from a career, an excellent career, maybe block them from a transfer because they're not getting good grade, because maybe they're not doing so well in some of the math course. So many people kind of dislike mathematics, right? So the teachers in mathematics division have to struggle to inspire them, like my wife, that she worked very hard day and night trying to find a good way, innovative way to inspire students, because a student, once you dislike a subject, you shut off your mind, say, I don't like it. Once you tell yourself, I don't like a subject, you refuse to learn it, right? So that is a vicious cycle. But today I want to tell you that it's not that bad. Actually, there's a lot of fun, a lot of good things could come out because of mathematics. So let's start with this page to follow up with the Los Angeles Times reporting. So many people will say, well, mathematics is hard, right? It's too abstract. I don't know why it is useful to have any connection to our daily life. So mathematician, as you see from this TV movie, like A Beautiful Mind, you think, well, mathematician need to be too nerdy, right? Not a normal human being, right? So, well, they're smart, but I don't want to be one of them, right? So on the other hand, if you talk to engineer or to other scientists, because we have taught mathematics so well, so many of them, they know mathematics as well as a mathematician. So we do not monopolize the subject, right? So many people, especially at Caltech, we used to teach this a huge class called ACM 95, of Introduction to Mathematics, Method of Mathematics. Because we taught them so well, many undergraduate students hate it, and they think it's very tough. But after they've gone through it, they went to college, to Berkeley, to Stanford, to Princeton, they found that they're much better prepared than their peer. So they move on, and I would tell you one example. One of the Nobel Prize winner in economics, he was a master student in applied mathematics, and then because he's interested really in economics, so our department chair, Jerry Witham at the time, advised him, you should transfer to MIT to study economics. Because he knows mathematics, he has very solid foundation in mathematics, he won the Nobel Prize in economics because of that. So many examples like that. So mathematics is kind of behind the scene in many applications, in movie theater, special effect, technology. I will give you many such examples. So then you may wonder that so why math is relevant, right? I have the title, but you may say, well, maybe just have the title to attract me to come here, but I don't see the relevance, right? So I'm going to show you that indeed it's very relevant to science, technology, to society, to many things. So one of the more obvious connection that people study physics and chemistry, computer science, you say, well, there's a lot of mathematics. Physics, you need to use equation, right? Newton's law. You use mathematics to describe it. It's a very quantitative description. Biology, right? Nowadays we have to dealing with a massive amount of data. You want to find out the underlying patterns, right? So there's a lot of structure, geometry involved. I will show you some of the examples. One of the Nobel Prize winner in chemistry, because he used distant geometry, so that enabled him to discover a new method that allow him to make a breakthrough. And also in Hollywood, and there's a lot of special effect that actually the people from UCLA, Stanley Osher and some of his students, some of the special effect, I'm going to show you some of the example. Actually, behind it was a differential equation, numerical method. So very sophisticated mathematics, because some of this special effect, you cannot really do it by real tag, right? Because it is too expensive, very hard to manipulate. But you can do it by computer through numerical methods. So there are many more examples. I can keep going on and on, like a Google, GPS. I'm going to show you some of this example, like a JPEG. We use image compression. You use a camera, right? You can use, now they have a very high definition camera, and you have to do compression and then transmission without lost much information. You can do very high quality pictures, and special effect in movie like a Titanic and Terminator 3, Cars, and medical image MRI, right? So a CAT, right? Computer X-ray tomography, and many of these behind them is mathematics, is the engine. And the last example, which is a very interesting example, due to the time limit, I will not show it. But in fact, many of us have to take airplane. I travel a lot. But so nowadays, if you go to talk a place like Boeing, right? When they design airplane, in the old days they have to blow the wind tunnel, right? You have to do a lot of test experiment through the wind tunnel. But doing one test of wind tunnel is very expensive. Now they do most of the pre-screening, the optimization through computer aided using computational fluid dynamics. So you can just narrow down the very few final design option, and then you do the wind tunnel, and that saves you a lot of time. And this is American Cup story in Switzerland. So this is a sailboat competition. It's a worldwide competition. You imagine that a country like Switzerland, there's no ocean, not next to the ocean, it's a dry land. How could they win the American Cup? Because a professor in EPFL, Professor Quattroni, is a friend of mine, he used a very sophisticated computational fluid dynamics software to design a boat that minimized the drag, right? So that have a special optimization design that enabled that the Swiss team win the American Cup. That become a big story. So, so why mathematics is so powerful, right? So mathematics, because it is provide a very precise description. It gives you the quantitative tool, right? So when you have some idea about something, you want to really pin it down. Mathematics provide the language, the tool. And also the computational method behind it. That's what we do in my Department of Applied and Computational Mathematics. So it is a combination of using mathematical idea to solve engineering scientific applications. So we trying to build tool that you can simulate real-life scientific event through computer, through very innovative algorithm. So behind it are all mathematics driven. So I mentioned physics, right? We mentioned Einstein. Today's Einstein's birthday. So Einstein was most famous for the discovery of relativity, right? General relativity. Behind the relativity, of course, first I have to have this ingenious idea about this concept about the physics. The curve will bend in space-time, right? But to describe it, to make it precise, make a very precise prediction, you need this differential geometry. You need a very sophisticated mathematics. In fact, I was told when Einstein was in college, he did not think mathematics is not very useful. He wanted to understand the nature, right, the physics. He said physics is more important, right? But at the end, he changed his mind. He said, no, actually, in order for him to make the discovery, he needs the mathematics, the tool. In fact, the mathematics he used is much advanced in his time. In fact, he's one of the pioneer contributor to the field of differential geometry because the Einstein equation actually generate a lot of activity it come back to inspire mathematicians to study this field, like the string theory or all these things are inspired by this differential geometry, by the relativity field. So there was a famous scientist, Wigner, there's a famous quote. He said there's unreasonable effectiveness of mathematics in natural science. It's because you would not think that mathematics could be so powerful, but in fact, it is very effective. It's so effective so that you think it's unreasonable, because it is true, right? So many people study mathematics. Some of them are more pure mathematicians, really driven by curiosity, right? You study mathematics because it's the beauty, right? The natural beauty, the elegance, right? the creativity, intellectual challenge, right? So a lot of people, like in pure math department, like my colleague in the pure math department, many people, like the beautiful mind, John Nash, these people are naturally like a genius. They're interested in mathematics just because it's the beauty, the pure challenge, right? But there's another kind of people, like our prime mathematician or many scientists, who use interest in mathematics because it provides a very good tool, right? It's a language, right? It's like when you speak, when you try to communicate with people, you need to have a language, right? Mathematics is like a language, enable you to communicate, right? Make a very precise description. It's the foundation of technology. So today I'm more focused on the second part, because that's how you can see the effect, how mathematics can change the quality of life. So let me give you an example. As many of you know, the computer, the rapid development of computer, how fast the so-called, the famous Moore's law, right? Every 10 years, there was you double the speed of a hardware computer, right? So many years ago, I heard even some of the prime mathematicians or the scientists say, well, as time in 20 or 30 years, maybe we don't need mathematicians, we don't need numerical analysts, because the computer is so powerful, we can solve it just by brute force, right? So we were a little bit, some of us a little bit scared. So that doesn't mean that we were out of job. There's no need for a prime mathematician anymore. Fortunately, not so. This is a very convincing picture, evident. So think about because as I say, in many applications, you need to solve physical problem. When you're trying to encounter to solve the physical problem, you need to solve differential equation, right? So if you're just using the sheer power of computer, but rely on the computer, the capacity doubling every 10 years, you only go by so far. Meaning that look at this chart, this chart. So you only if not because of the innovation or new algorithm, new numerical method, you're not going very far. So the improvement from 1945 to 1978, right? So the progress made through a better method, better numerical method, it is 40 times more than the speed up driven by the hardware development. So you can see that. And then the second example is more intriguing, more convincing, more surprising. That we know that factoring a large number, it is a very important application in many, like in designing a code, like breaking a code, right? So what your ability to factor a large prime number, very fast. So this is the engine in many applications, right? So but over the year, if you think about a algorithm back to 70, like 40 years ago, right? 40 years ago. So you use an algorithm developed in the early 70s, and you may take 300 years to factor a huge number. But now, because of the innovation, the new method available, you can do it in 1 day. So the improvement, the speed up, just by algorithm by the algorithm improvement, you can get the 120,000 times faster. Think about that. So that speaks the power of mathematics, right? So it is I can give you many examples. For example, we talk about the number theory. Right? So many people you think, right, number theory is just a pure curiosity, right? What does it has anything to do with a daily life? Well, during the World War II, in fact, there's a very famous story that the American and the Allied and the British break the code, the German code, because the submarine they attacked the vessel across the Atlantic, because Alan Turing, Turing is really the founder, the inventor of the computer, right? So he designed using a number of techniques, numerical techniques based on number theory, that he enabled to design a number of code breaker that enable us to break the code, and that also led to the development of the first computer after the World War II. So behind it is number theory. So I mentioned that there's several Nobel Prize in different fields. They really use mathematics structure. Like in this case, the Nobel Prize 2002 in chemistry, they actually look at this here. They're trying to study the protein structure, right? The nuclei in the protein. How do you classify a large set of protein? Right? As I said, now they have a huge amount of data set in the three-dimensional space. Very complicated. How do you quantify how do you extract the structure? So he developed a new method based on the distance, the pairwise distance between the two molecule, right? So based on this complicated three-dimensional structure using distance and geometric concept. So although he is a chemist by training, but because the mathematics, the knowledge that he has throughout his training, right, that he enabled him to make this breakthrough and eventually won the Nobel Prize. So this is a 2003 Nobel Prize in medicine. So this is awarded to these two scientists who actually invented this MRI, the magnetic resonance imaging, right? So this is so many of us, some of us, you may have the experience that if you need to go through a examination of that you think, you may wonder what is the mathematics, or more, what is the science behind this MRI machine, right? Actually, it turns out that you can think about mathematically, it's like this. So this is the subject to be examined. So you want to take some cross section in your body, right? Basically, you are only allowed to shoot some rate, right? You shoot some kind of rate. It's like you think about, you discretize your body, the cross section. So you have a number of discretized elements that you would like to, this is the image you would like to recover, for example, right? So you basically take some kind of diagonal or cross-sectional measurement, right? You take a one-dimensional measurement, but from different angle, right? So basically, you can do it in this shape, is a radial measurement through different angle, like you take the discretized angle, like 120 degree, and then each angle you shoot a one-dimensional measurement, average. From there, you recover the image. So behind it is because the image, because your body have a different organ, they have a different refraction, so that it introduce a different gradient. From there, you can recover the image through this one-dimensional measurement. And there's a latest development, how do you generate the measurement? If you generate the measurement in a smarter way, guided by optimization mathematics, you can actually, with a fewer measurement. Because imagine that if you have a small kid, small children, that who may not be able to sit still through that process, it may take 30 minutes to the exam. The kid may move around a lot. So then you want to minimize the number of measurements, minimize the time it takes, right? So modern mathematics actually lead to new technology. I will come back to this later. So I mentioned about the Nobel Prize in economics. So it was awarded to these two gentlemen, Robert Merton and Myron Scholes, right? Actually, this famous work was actually developed by Bragg and Scholes, the so-called Bragg-Scholes equation. Unfortunately, he died 2 years before the Nobel Prize was given. So, and Robert Merton, it was a Caltech alumni. It is from my department. I mentioned that he was doing a master degree, was doing a PhD degree in my department back in the late 70s or something. But because at the time he told our department chair, Jerry Rhythm, that he's really interested to study economics. They're using mathematics to study economics. So Rhythm recognized that he's a very rare talent. He said, well, of course, you should really understand what is the most important subject in economics. Of course, mathematics is important, but it's more important you should understand what is the right question to ask in economics. So he sent him to MIT. The MIT economic department is a very strong theoretical foundation in mathematics, very strong. They have a tradition to produce a Nobel Prize winner. So and he went there. He did a PhD, and then he using this Bragg-Scholes equation. He found that there's you can use this Bragg-Scholes equation. This is a stochastic equation that tell you a more precise scientific way to give pricing of option trading, right? And so in fact, that completely revolutionized the whole option trading. Before, you don't really know how to set the price in a fair way, right? By using this stochastic processing, stochastic equation, they completely standardize the industry. In fact, that I think this few gentlemen set up a firm. I think it's long-term capital, but that doesn't do very well during the Russian. They made the wrong bet at some point, but they did very well for some time, and then because there's a lot of volatility. So in fact, some people blame the mathematical finance for the crash of the 2009 because the people getting too greedy using the mathematical model. So I have a number of PhD students who move on to the Wall Street and make a lot of money. And some of them complain to me that, come back to talk to me that, he said the quantitative analysts, they got all the blame if the trade was not going so well at the end. If it goes well, the trader take all the credit. Say, I made the right decision. Mathematician only provide one of the evidence. So this is still a very new field. So how mathematics can be used in finance, the quantitative analysis, because the data has been very limited, because we only use this kind of mathematic guided trading for a small number of years, and there's a lot of human factor involved. You cannot just use a simple differential equation, and those parameters, the volatility, has to be measured from the real data. And in fact, my former student, Gang Hu, came back to Caltech to give a talk a couple years ago. He said, this is very dynamic, because once everybody recognize this is the model to set the pricing, everybody jump to it, and then the model change. It's not the right model anymore, because then the situation change. So you have to use a new model, right? So that's why it's very complicated. So for many years, people always think that the real estate price only go one-way street, only go up. So they underestimate the volatility. Of course, the greedy also come into the factor. So after the crash of the 2008, 2009 stock market, the financial market, people come back to this, really trying to understand the risk management. So uncertainty quantification become a very important field. How to understand stochastic effect, stochastic differential equation become very important field. So I think that whenever you see something went wrong, it's not because just to blame somebody. It's because we do not completely understand the situation that call for the need to develop a better theory, a better model. So I would say there's more opportunity there. So these are another example that mathematician turn rich, right? So these are two very well-known mathematicians. James Simon is a very famous mathematician, a geometer. I think he was an MIT professor. There's a very famous Chern-Simon theorem. But then he decided to leave the field of mathematics in the late 70s or so, to develop one of the first hedge fund. Maybe he's not the first hedge fund founder, but he's the first hedge fund based on mathematics, quantitative analysis to do trading. And after some up and down, he made huge amount of money. He founded the Renaissance technology, right? So make huge amount of money. So D.G. Shaw is another professor, a mathematics professor from Columbia University. Again, these people, because they understand mathematics, they found a very good model to make trading decision completely based on computer, no human emotion. Because in many cases, when you see this TV or movie showing this Wall Street trader shouting in the room that, you do this, do that, right? So I was told by my student that, the Wall Street people hire football players. They don't hire mathematicians. Only recently they decided they think mathematicians or physicists, well-trained intellectual people, can make a better judgment. Because it's a very competitive field. You have to be very strong mind and make quick decision, very quick decision, right? Because otherwise, other people will make the bet ahead of you, and that a split of second decision can make a huge difference. So they typically have a very short lifespan, this trader on the Wall Street, and maybe 10 years, and then they make enough money and they retire. But you have to physically, mentally very strong. But nowadays, the mathematics, computer trading changed the whole landscape. So you need intelligence, you need mathematics. You can make the trade in the computer room by studying the market carefully, right? So these are all examples that mathematicians can not only change the way we do trading, but also the personal life, they become a millionaire, right? So I want to say something about that. So what is the mathematics behind financial mathematics? It's really stochastic calculus, partial differential equation, probability theory, statistics, computational method. So these are the methods that enable you to do quantitative analysis. So we're talking about the option pricing. This is the Black-Scholes equation, the derivative option. So because of this industry used to be very ad hoc, become more standardized due to the mathematics. So let me give you a few example, concrete example, to walk you through a little bit more the mathematics behind it, right? So GPS. So a lot of people use GPS, right? Your cell phone have GPS. If you drive a car, if you don't have a GPS, many people don't know how to find their own way. So, so GPS become part of your life. But you may wonder, what is mathematics behind GPS? So basically, it's like this, right? You have in the circle here, it's just like the Earth, right? So there's a blue dot here. So it's something, it's a target you want to track, right? So the question is that imagine that you have many satellites orbiting the Earth, right? So you want to track a particular target on the Earth, either driving or somebody walking. The question is that what's the minimum number of satellites required to track that person, right, or the object, right? So that becomes a mathematical question, and then that mathematical question. So there's a number keep changing here. It depends on where you are, because of visibility and so on. That number may change, right? The minimum number of change, right? So you may think, well, what is the mathematics got to do with this? So it turns out that you can. I apologize for this slide. It's a little bit more dense, but this gives you, it's a Wikipedian version to walk you through the mathematics behind it. So imagine that there was 3 or 4 satellites, right? So you want to keep track a object somewhere in the Earth, right? So basically, of course, the object you want to track have to have a device, a GPS device, so that you can send a signal or receive a signal, right? So that's how you communicate with a satellite, right? So the satellite, basically, if you communicate with the first satellite, you compute the distance, because the time difference. You send a signal, will travel by the speed of light, right? So you send out a signal to the satellite come back to you. You can measure the distance you travel. So you log out. So you can measure the first distance, the distance from here to here. And then the distance to the second satellite, the distance to the third satellite. So basically, once you know the distance between the object, your receiver, and the satellite, you know that you are located in a surface on the sphere center at the first satellite with the radius given by the distance, right? So you know that that point will be somewhere on the surface center at this satellite with the radius that you know you can measure the distance. The same thing here for the second satellite. There was another radius, not a circle, right? And then the two circle intersection, you get the two sphere intersection, you get the circle, right? And then it's the same thing for the third satellite. So the more satellite you have more constraint, and then the intersection of this curve, it is your location, right? So in fact, mathematically, you can turn it into a quadratic equation. So you have 3 satellites. You know the position of the satellite, x1, y1, z1, x2. You need 4 satellites minimum, right? Because there was a time bias. There's a time bias. So this is the location you want to track. You want to find a location x, y, z. You label them the x, y, z, right? So you through the measurement, you send a signal receive. You can calculate this distance d1, d2, d3, d4, right? So this is the distance between x, y, z. It is unknown, right? But the satellite position you know, right? So you know this is the distance. So this is the distance you measure, right? But there's a time bias because it's not completely synchronized. The clock of your GPS and the clock of the satellite. So you're assuming that all the different satellites have to synchronize the time, right? But then there's a bias. So you don't know the bias between your GPS time and the satellite time. There could be a small bias. So there's 4 unknown. So x, y, z is unknown. The time delay, it is a unknown. C, it is the speed of light. The distance is something you can measure. So in principle, you have 4 unknown, you have 4 equations. But it's a quadratic equation. You may have multiple solutions, right? You can eliminate one of the unphysical solutions that are not landing on the Earth's surface. Will be somewhere in the planet. So very easily to exclude the other unphysical solution. So you need 4, but the more measurement the better. You have a faster method, more accurate to locate the position. So you can see behind this. So of course the real challenge is the computer solve this equation fast, right? Because as you're driving, as you're running, you need to recompute it, right? So I remember when we watched the James Bond movie. So if somebody stuck something to you or to your car, and that they can track you because of the GPS, right? So that's why the Bin Laden will refuse to use the mobile phone when he's hiding in the mountain, because once you have a mobile phone, then they can lock you down because you have a signal. They can track you to measure the distance, right? So you really need to have a receiver to receive, or somebody can track you down. Otherwise, they cannot calculate the distance, right? If you know you don't have the distance, you cannot solve this equation, right? So all these things are mathematics behind it. It's very. So the next thing I would like to talk about is the network, the Facebook and the graph, how the graph theory can be useful. So the graph theory basically said that, well, we talk about the discrete world, and not about differential equation now. So you have nodes, you have edge. So how do they make connection, right? So this graph can be connected, could have no direction, could have direction. So the connection does not really depend on the distance. As long as there is a connection, that it is a graph, okay? So we can see all different kind of graph. It will be a train map, it is a graph, right? This is a social network, if you use a Facebook, for example. So there's some, like in college, if some guy is very popular, you have a lot of people connect to you, right? And then you connect to another cluster of people, right? So then they build a social network. So actually, it's very interesting. Let me use a Google page ranking as an example to walk you through. So Google was founded in 1998, relatively recent, only like 15 years ago, right? So I remember one of my friends is a professor at UC Davis. He said that when they first founded when they're still developing the idea of Google, one day they walked to Professor Jim Golub at Stanford University. He's a master, is the pioneer in the linear algebra, numerical linear algebra. So they realized that to do the search engines really down to linear algebra, how to solve the eigenvalue problem very fast. So he asked some question that my friend Jun Chao Bai was was visiting Professor Jim Golub at Stanford. So I think one of the Google scientists, the founder, walked to the office of Jim Golub and said, could you help us to develop some fast algorithm? There's a great potential, commercial potential. Jim Golub was saying, oh, I'm too old, I'm too busy, don't bother me. But you can ask my friend, Zhao Jun, that maybe he could help you. So Zhao Jun said that he was young at the time. I'm too busy to writing research paper. I don't have time to work for Google. But he kind of regretted later, because if he worked with Google at that time, he probably very, very rich right now, you know. So, but at the end, it is about solving a linear system, a large, huge linear system. You solve a graph, many connections, but you want to have a real time to track down. When you click something, you get to the side you want very fast. Behind it is mathematics. For example, if you click PCC, you type Google PCC, this page will come up, right? So how does people use this page ranking to decide which site is more important? Because it has a lot of commercial. How come Facebook becomes so valuable within such a short time? Because a lot of people use it, right? When a lot of people sign to it, you can do advertisement, and then that translates to money, to revenue, right? So a lot of people trying to work very hard to boost up their page ranking. If more people point to your website, if you find a way to make people curious. So that's why at the beginning people give you free service, right? So thank you. So you don't need to pay anything, like Facebook is free, right? You think, how come that's such a good thing? They provide such a big account like Google, Gmail, and Facebook, everything free. Why do they do that, right? Who pay for this? But because when enough people use it, then the revenue comes. They refuse to advertise. If you see the social network, the movie, right? So Mark Zuckerberg was very smart. He refused to advertise, trying to make money too fast, trying to increase the subscriber, and only up to a certain point, and then he tried to put in a commercial aspect. So this is the way they rank the website, the important of the website. Depends on how many people pointed to you. Of course, there's a mathematic, more precise way to compute it. For example, is it B and C are the big, for example, this is a Google map or Facebook. A lot of people connect to Google because they use Google a lot. And that depends on how many people pointed to you, back pointing to you. And that there's a way to calculate how important you are. That's a ranking, right? For example, when you type certain keyword in Google, right? And then the first will be 10 or whatever number of most popular website will pops up. How Google find out? There was an algorithm, right? Because they see this algorithm this keyword. Many people pointed to that website. They think very likely, maybe that's what you're looking for, right? So that's why in many cases, that you found what you want, right? In the first page, you find one of the website that's what you're looking for. Even you type the wrong letter, right? You miss a spelling or something. That's okay, because they're smart enough to figure out. So let me walk. So what is the mathematics behind the page ranking, right? So for example, let me use this graph to illustrate. For example, we have a number of websites. I labeled them 1, 2, 3, 4, number 7, and there's 2 groups. This is first group. There's a lot of connection in here, but 1 then connect to 5. That's the only way from 1 connect to 5. For example, you imagine maybe number 1 is the chairman or the president of the PCC student union, for example, right? And number 5 may be the Caltech student union, right? The president. These two can communicate, right? Not everybody here communicate directly with Caltech student, right? But this student have a lot of connection with the PCC, or for example, other club member, right? So there's a PCC, Caltech has its own internal network, right? So this is how they calculate it. They will depend on how many links you go out from 1, right? 1 link to number 2, number 3, number 5. So then there's a matrix here. So 1, meaning the first row, connect to number 2, number 3, number 5. So assuming that each one have equal weight. This is an example. Doesn't have to have equal weight. You have a different weight. For example, so the first row, you have 1 connected to 2. I have 1/3 here. Number 3, 1/3. Number 1 does not connect to itself, so it's a 0 rank. And then come the number 5. This is number 5 here. The similar number 2 only pointed to number 1, so it's only the first one has a 1, and then the remaining have 0. So similarly, you get the idea, right? So you get the connection matrix. This is H is a hyperlink matrix, right? So then you're trying to develop an iterative scheme. You say, well, if you have somebody give you some ranking, you would, through this matrix, you would tell you how does it connect to the outside. So you would develop an iterative method at t equals 0, at the initial guess, you say everybody is equal important. We don't know which one is more important. So initially you set the initial condition for this pi at k equals 0. Everybody equal. There's 7 websites. So 10 divided by, or 7 divided by 10 is 1.43, right? So then you apply this to this matrix. After a few iterations, it converges. Then this is the number it converges after 2 iterations. And then based on the number, you find which one has the highest rank, right? So you get this one, the number 1, ranking number 2, and number 3. Then you get the order. Just give you an illustration. There's many variations to it. Depends on how you assign importance. So it all has to do with this. How do you put the weight? How does this connection work, right? So this direction is very important, right? So as I say, if people who understand how this page ranking works, then you can actually manipulate. You can make a lot of profit, a lot of money, right? So some people actually, if you have a website, you have a lot of people sign to you, you can actually sell the website to somebody who wants to get more citation, more traffic, and you can make money that way, right? So again, like if people use Facebook, and you have, as I say, you may wonder why Facebook provide all the service for you for free, because you share a lot of information among your friends, what you like, what you don't like. They have the information. That information has a lot of commercial value. Then they can sell to different advertising company, right? Like a movie rental company, or maybe shopping, like a clothing company. Then they can sell advertisement to you, target to your particular need, right? So that's this. So now let me show you some other example how mathematics can make a difference. So these are 3 mathematicians. Immanuel Kant, they used to be my colleague at Caltech. I actually recruited him to Caltech in 2000, and he moved to Stanford University about 3 or 4 years ago for family reason. And Terry Tao, the professor at UCLA, he got the Fields Medal. It's very famous. And David Donahoe is a very well-known mathematician. He was his advisor. So they developed something very cool called compressed sensing. So let me just walk you through one concrete example of how compressed sensing works. So many of you probably heard about Netflix, right? You rent a movie, online renting movie, that used to be Blockbuster, and the Blockbuster will be went out of business now. So they have this very advanced online, very cheap, right? And then if you rent a few movies, and they will suggest, maybe you're also interested to see this movie, right? How do you find out, right? So that is the mathematics behind it. So actually they gave out a prize. They have this ranking scheme. within Netflix. But they realized that their method is not fast enough, not accurate enough. So they have a context. If you Google Netflix price, it has a whole page explaining the history. In 2006, they gave out a 1 million award to the many teams around the world, whoever can come up with an algorithm that can 10% faster, more accurate to complete the ranking, then they can give $1 million prize. So many teams participate in this. It's a huge news. And basically, let me explain it to you what was going on. So basically, they say, well, I have a 17,770 movie. They have the data. They have a lot of data. And then they have a 480,000 user, right? People who had this data. But of course, each user only ran a few movies, or maybe only willing to rate a few movies from 1 to 5. You say, what is the most favorite movie? What is the most disliked movie? So based on that, you want to complete the whole matrix. Basically, you want to know everyone what is your rating for all these remaining movie. Although everyone can only rate a few movies, right? So there's some few outlier. One guy maybe just hate this idea so much, he rated 1,000 movies, 10,000 movies. Of course, he had not seen all those movies. But most people only rate maybe 10 movies, right? They watch a few movies, they responsibly, right? So you have some corrupted data. But basically, they have about 1,000 million rating from this group of people. And from there, they want you to predict 3 million rating of the higher accuracy. So they had the data. They had the data. People already returned their poll, their rating, right? But they did not give them information to you. They ask you based on some partial information, right? They only give you 100 million rating, right? From there, they want you to predict 3 million rating, but not given to you accurately, right? So if you multiply this number, the total number of movies by the total number of users, you have an 8 billion number of ratings. So meaning that, think about formulating in mathematics. So you have a huge matrix, right? But you only know a very small number of elements, right? These are the black spot are the rating that you return. But you would like to know what do they like. For example, this is the number of users, this is the number of movie, right? But you have a lot of empty spot that you want to fill. You want to find out what are the people interested based on the few measurements, right? So this has become a linear algebra question. You want to approximate a huge matrix by a low-rank approximation. It's a long matrix, a long skinny, and then a long thin matrix, right? So the R is small, R is the rank of the matrix, right? Because R is much smaller than the size of your matrix, so you can develop fast algorithm to do a completion. So there was this three mathematicians I mentioned earlier. They developed very sophisticated minimization problem by minimize the nuclear norm of a matrix subject to the data you're given. You can actually, knowing the fact that the matrix is not arbitrary matrix, it's a low-rank matrix, you can actually recover almost exactly with a very high probability with a very small number of measurements. So that is very amazing, right? So there's some mathematics behind it. So the nuclear norm, it is you have to do a singular value decomposition of a matrix, and then you sum up all the singular value. That's how you get a nuclear norm. So for those of you who have not studied linear algebra, you probably do not understand this slide. But for those who have studied linear algebra, I want to tell you it is important. It's useful. Although when you learn it, the first time you learn it, you say, so dry. Why should I bother? But a lot of the Google stuff, it is behind it is linear algebra. Okay, it's very useful. So let me show you some application of this kind of algorithm. So for example, the left picture here, this image, it's only 20% data. You're missing and it's corrupted by noise, right? Using this kind of a low-rank approximation, you recover a very clean matrix, right? There's a lot of information here, but some of them, of course, there's some little bit blurring here, but compared to the original signal, you get a pretty good recovery, right? Because it's not completely random, right? Not completely arbitrary. They have structure, it's a low-rank structure, right? So you can also do another kind of a factorization. What happens if the matrix is not low rank, right? But also have some very low rank, but plus something sparse, a few singularity here and there. So then they can also modify the algorithm by combine this low rank with a L1 minimization to pick up the sparsity. So this is the compressed sensing stuff. Only happened in the last 10 years, or less than 10 years, become a very fashionable field. So let me show you the application that this is a surveillance camera. Suppose you're in a shopping mall, right? You have taken there's a surveillance camera everywhere, right? So you want to see, well, you want to see what are the people who just move, the stranger, right? Maybe the potential terrorist. You will say, well, if this is, you get a frame of a slide, the through different time, right? So these are the background. So you can separate the background. The background are the people walking here, they do not move around, right? This guy's standing there doing nothing. So this is considered as a background. But these people walking through, this is the low rank, this is the sparse. You can actually single out the two set of data. There's many interesting applications, of course, for security reason. You want to target somebody from the airport, you say, well, there's some people maybe very, very strangely walking through. You want to identify that could be a suspect, right? So these are the very useful application. You can also do a real-life denoising video. So this is a very noisy video, and this is the recover one, right? So you remove the noise. For the one that's corrupted from the left, you get a very clean video back on the right. So this is the one that again, is this a surveillance camera, right? You see somebody walking in, you get the mail, and they come back left, right? Somebody maybe walking to your math office, pick up the mail and left. So you can see the background has not changed much, but that single person, you can single out on the picture on the left. You can have a very compressed version. You don't need to store the whole data. So this is very cool application. Only 10% of measurement. You only have very few data, right? So there's other application in image compression. For example, this is a two image. This is the original image that take a 262 K bytes to get this resolution. But now using the wavelength and multi-resolution technique, you can compress it to 8 gigabyte, but with almost the same quality. So that's using a compression. So before 2000, people use this cosine transform to do image compression. If you're using camera or using whatever, you need to use, this is a 3 megabyte original cameras, very high original image, very high resolution. So if you use a 19K gigabyte JPEG, which is using wavelength, you almost get the same quality. You get a huge amount of compression. But if you use the old version JPEG, not the JPEG 2000, which is based on cosine transform, you get a very poor resolution, right? So you can see because the modern development of a wavelength multi-resolution analysis, due to this, Ingrid Lubitsch is one of the pioneers, a mathematician. He used to be at Princeton, now moved to Duke. And this Charles Chu, he's the one that served on the JPEG 2000 committee that responsible to introduce the new technology wavelength to enhance this image compression. And I mentioned about how mathematics is used in Hollywood in special effect. So these two gentlemen, Professor Stanley Oshie is one of my teachers at UCLA, and this is his former student now, Professor Stanford. They have using this level set method doing image. So this is a very famous picture. They use this LA riot. So some of you may be too young to know the story. In 1992, the year before I came here, there's a huge riot in Los Angeles because of police beating. There's some mishandling of a civilian case, and then lead to a riot. So there's the civilian camera, I think from the helicopter, they took this picture. There's some guy who dragged down the driver, a truck driver, and beat him, right? It's really a crime. And then the police identify a suspect, but the suspect says, no, that's not me. How do you know that from such a high, from the helicopter, how do you know this is me? So then they ask for the technical witness, right, advisor from Stanley Oshie. They use the image enhancement technique. Then he found out that by enhanced image, although you took the shot from so far away, they identified there's a tattoo in his left arm. So you can see that that tattoo after the enhancement matched the real tattoo, of course. And then this is the first time I was told the U.S. court allowed such a high-tech evidence, use it as an evidence in the court, and then he was indicted. This may not be the only evidence, but it's a very important piece of evidence that make him. So if that make mathematician become so well known, Stan Oshie's image appear in many popular magazines because after that everybody convinced, oh, mathematics is cool and can do a lot of things. Yeah. So this is the image. You can see that this part is overexposed. This part is underexposed, right? So after the enhancement, you can see that you get the right balance, right? You get almost close to the original. You can recover some of the shaded area from here, right? This one is not overexposed. So this is a very blurred, but by take a camera, you shake your hand, you get a very blurred image. After the enhancement, you recover very sharp image, right? A similar thing here. So I mentioned that many mathematics has been used as a special effect in movie industry, like in Pixar, right? And these are some of the movies that the way mathematics use. So I can show you a movie that this is using the effect of level set by these two gentlemen, Raffle and Stan Osher. It's very hard to make this kind of a special effect in the view experiment, but this is all computer made animation. You can see, let me play to you again. It's very, again, you're solving through dynamic equation, a multi-phase flow, but using this image enhancement, you do something very cool. And this is the special effect in one of the movies, The Lighthouse. They're very hard to make this a true image. Imagine in the ocean, right? You cannot control the weather, right? There's a lighthouse. They need this storm coming in, and these two gentlemen. The special effect come to Raffle. They made this a very beautiful movie, a special effect. So this is this is almost my last slide. So for many years, people may think, during my time as a graduate student, mathematics seems to be it's very hard to find a job, right? It's not a very popular subject. But in 2009, the Wall Street Journal, mathematics was ranked number 1, the best job, right? And actually, as a statistician, for the first top 3, are all related to mathematics, right? So you can see the time has changed so much. The worst is the lumberjack, right? So ranked 200. That may not be fair, but so some of the traditional way of thinking, people study mathematics, you may want to be a high school teacher, right? A K to 12, or insurance industry, and maybe possible aerospace industry, auto industry. But nowadays, there's many other opportunities. You can do biomedical, pharmaceutical, communication, finance. Many of my students went to finance, economic, and there's a nanotechnology, entertainment, and mathematics really opened up a lot of, I think more and more the industry realized the power of mathematics. And not only the tool that we brought useful tool, also the training, the mindset, the abstraction, right? Analytical skill. That's why they want to hire a lot of PhD that we train at Caltech with a Primath background. So I guess that's all I have. I hope that I can convince you that mathematics is not that dry. It could be useful, it could be fun. Thank you very much. I'm happy to answer a few questions if you have some. I should add that some of my own PhD students, my postdoc, has some of them went to ExxonMobil, become really the chief scientist technology in develop the next generation of a flow simulator. Some of another ex-postdoc went to a seismology software company, and he became the chief technology, the global CGG Rarita. So for many of them, this is the first time they hire a mathematician. But after they hire somebody, they see how great they can operate, and they completely change their view towards mathematicians. After that, they hire a whole wave of prime mathematicians, and because that really translates to productivity, competitiveness in the industry, it really completely changed the landscape. So I think more and more the industry recognize the power of mathematics. So if you're interested in doing mathematics, if you're good at mathematics, don't give up, okay? I think there's a great potential. Even if you don't want to be a mathematician for your career, but because you know mathematics, you master, that really could be your edge and put you in a more competitive compared to other peers who doesn't know mathematics, because then they may shy away from another opportunity that you could take advantage of, right? Yeah. Any questions? Because I was told I should leave a lot of time for questions, but if there's no question, it's all understood. I guess you completely sold, right? Yeah. That's good. Yes? Using what? Oh, yeah. Say it again. What's it? Oh, they discontinue using that? Oh, okay. Okay, exactly, because that's a very good point, because once you know the formula, people can manipulate it. Then it's not the true, will not reflect the true ranking anymore. So what we showed just as an illustration, I don't think that is a very naive formula. Yeah, I'm sure that they will keep it a secret. It's a pattern information. Yeah. 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 That's why I said it's an evolving market. It's like in this Black-Scholes equation. So people use that to price the option price the derivative. But once everybody knows this is the formula, everybody use the same formula, then they will not be true anymore. There's a strong bias. It's not independent. Because the fact that they derived that the Black-Scholes equation assume everybody act independently, right? We don't know each other. And then you can characterize by boundary motion, by stochastic. But when everybody predicting, expecting you do the same thing, then there's a strong correlation. So the model change, right? So all these things are dynamic. So that's why there's a lot of human factor involved. It is not as simple. So mathematics is important, but you cannot solve the real world problem by mathematics alone. So I should put the carrier. It's very important. Yeah. Yes, there's a question now. No, but I think Professor Caltech was, I think Joe Shepard, he was called to that investigation because exactly. So there was this combustion, this detonation. When you're under high temperature, high impact, so a lot of constitution relation in the people use the traditional, conventional theory will break down. So that they get the wrong prediction. Yeah. But I'm not expert in that. But I think my colleague in aeronautics, he was involved. Yeah. In fact, not only that example, like people in the national lab, like imagine there's a nuclear stockpile. Every year, the director of Los Alamos need to sign some certificate, make sure that the stockpile is safe. But that is a big uncertainty because how do you know those nuclear stockpile, even though it's not being used, there's a chemical reaction under different temperature over the time, so it could be very unsafe, right? You cannot do tests, right? You're not allowed to test. U.S. already signed the test to ban the nuclear test, but you can do a lot of computer simulation. But you don't really know the equation. The equation, a lot of those coefficients are unknown. The thing happened at such a small scale, the molecular nano scale, that the couple chemistry and a lot of material fracture. It's very complicated. The conventional continuum mechanic base are really wrong. So you have to go back to atomistic and molecular model, multi-scale model become very important. How do you predict uncertainty across scale is one of the things that Caltech, some of my colleagues in aeronautics, Michael Ortiz, they got a huge grant from DOE to do this kind of prediction. It's very tough, very complex. The real world is very complex. What I show you are some of the simple examples that are not so complicated involved because that will involve much more physics and mathematics at a much deeper level. It may not be appropriate for this audience today. Yeah.
I always thought that's just it's just my opinion, 1% opinion.
Yeah.
But this kind of rate, so maybe I don't know when. Maybe I already passed. I don't know. Okay. I always think we have a car running real fast on the freeway. Then the car will start fly in the air. I don't know when the government will open this area later. All the people start fly their own car on the freeway. Maybe just the degree is maybe higher than 3. Beauty that high. From city to city. That's where my opinion. What do you think? Is it possible?
I think that's like you live from 2-dimensional to 3-dimensional world, right? So when you drive on the freeway, it's 2-dimensional. You cannot overpass people. But once you're doing that, there's all kind of, we have airplane, right? You have to regulate the traffic. right? I think you have more problem because you will get traffic jam, you get crash, right? You don't have order, and unless you completely computerized, no human involvement. You have when you're driving on the freeway in the rush hour, a lot of emotion involved, right? People trying to cut you, you will react. How do you regulate this, right? If you go at least on the surface, you cannot just crash into other people. And when you live on the third dimension, and then people, how do you prevent people will take up the same time to crash? And there's a lot of problem. I don't think this is way beyond me, but I don't think that it's anytime soon. Maybe it's just way past our time.
Okay.
Yeah.
Yeah, I remember watching the Back to the Future movie, and in 2015 they show us with the flying cars.
Yeah.
The thing is, if like cars fly,
Yeah.
you don't have to go on specific roads. Like right now when they're on ground.
True. Yeah, when you have only a few cars, then of course you can do it. With a lot of huge space, right? But when you allow everybody to fly, then there's a lot of possibility to combinatory possibility, and that's very hard to regulate, you know. But this, I think this is not just a mathematical question. It is really a very complex social network. Yeah, this is way beyond our imagination. Yeah, I don't think that would be the problem. That would be the way to solve the problem, the traffic problem. Yeah, yeah. Only a very few people, very rich people have your own helicopter. Then you can, but when everybody rich, everybody have their own helicopter. Then it's not a lot of traffic jam either. Maybe taking the freeway is the fastest way, you know. Right? Yeah. So only very few people have the privilege. Then it's fast because you have the privilege. Not everybody can fly, can afford to fly, right? So but if everybody can fly so cheap, then it may be not economic anymore, right? Yeah. Yeah.
Are you familiar with the flower of life, that image that I posted in?
No, I'm sorry.
No? Oh, so
Yeah.
I was going to ask how you've seen it used in mathematics, because I did notice there was some sort of relevance as far as GPS goes and the pattern of
Okay.
the flower of life.
Yeah, I can see some very nice, so similar patterns. Yeah.
Yeah, so I was
Yeah.
wondering if this was used with that or not.
That's not my specialty. But a lot of pattern, especially in crystal, right? The crystal structure material, and they use that in water. There's a beautiful crystal structure. And there's a very beautiful documentary I've seen by Japanese scientists. If you talk to the water, the molecule, they have life. They change. If you talk to them in good word, you praise them, and the crystal structure become more and more beautiful. They have more life. If you curse them, you step backward, you're ugly, and then they shrink. They're like a child. If you treat them nice, you give them laugh, and they grow beautiful. Yeah.
There's a test with rice you can do with that.
Exactly. In the same document. Yeah. It is really amazing that you think there's no life in this. There's life in every level. It's beautiful. Yeah. Yes.
Can you talk about the math behind self-driving cars?
I think that is the math is more in the control. So some of my colleagues, one of the department that we have the control and dynamic system, is that you need to do a lot of. It's like the GPS, right? It is exactly there's more. You have to send a lot of signal to detect. You mean unmanned driving? You mean there's a context. So based on the camera, you're surveilling the neighborhood, right? You make a decision. What is the optimal object? There's a lot of obstacle, right? So this is more than mathematics, but a lot of the control theory are behind our mathematics. A very sophisticated mathematics involved functional analysis. Yeah.
I think I can actually answer this question.
Okay, please.
So I'm actually, in case you guys are wondering who I am, I'm the webmaster for the engineering club. We were actually entrusted with the project from, I guess, in association with NASA, and the computer science club is also helping us. But they want us to design a common telescope, which is basically we talk to the telescope, and the telescope's going to kind of look around and find stuff for us. So instead of us actually controlling the telescope typically with like a little control, we would tell the telescope like, hey telescope, find me the moon. So the moon would, the telescope would actually calibrate the sky and actually look at where things are. And then once it's done calibrating for about 5 minutes or so, I can ask it, where's the moon? And using GPS and as well as the images that it's been given, it'll find the moon for you. I assume that a car would work the same way. It would see
Yeah.
its surroundings and see that it's actually safe and maybe talk to the other car
Right.
to go above it.
Yeah.
I imagine that's how it would work.
Yeah, I think there's a lot of things to do with artificial intelligence, right? This is part of the branch in computer science, or EE. Yeah. But a lot of mathematics is used already submerged in this different field, in different subject of engineer. But you cannot use mathematics by itself to solve this problem. You have to use additional technology, right? So artificial intelligence, control theory is very, very important. Yeah. Yes, there's two questions. Yeah.
How do you turn something abstract like math, you know, the equations, onto something physical like the technology we have today? How does that work?
Say it again. The question is.
How do you turn something like the mathematical equations into something physical in our world?
I think it is the opposite, right? Mathematics is a language to describe the physics. Sometimes you can discover new physics through the deduction of mathematics, right, of equation. But I think more naturally should be you understand, you're given a physical scenario, you're trying to develop a mathematics to describe the physics. And then you want to verify with experiment to see if that's the right set of equations, right? So maybe through mathematical deduction, you can discover new physics, like Einstein, what Einstein did, right? So he had this general relativity completely beyond the Newton theory, right? Newton's law. And then he made a very concrete prediction. And then you have to do this experiment to verify whether or not his theory made the right prediction. So it takes a few years in the right moment to verify his theory. Then he becomes famous. Until that, nobody believed that he could be an idiot, right? He could be just crazy, right? But then people realize he's a genius, right? So in this is the case, very good example that mathematics, through the abstraction from physics, and you can make a prediction. That's the best kind of mathematics, right? But you have to work with physics hand in hand, right? In many cases, it was done by physicists, not by mathematicians alone, because mathematician does not have enough physical understanding to make that interpretation, the observation. Yeah. I think there's a question down here. Okay.
Are you familiar with Gödel's incompleteness theorem?
No, I heard of that term, but I don't know that field. In what subject is that?
I'm not sure exactly, but it's like, I think maybe prepositional calculus.
Uh-huh.
I'm just wondering if you might have some thoughts on whether or not it related to the observer effect that's seen in like quantum physics.
That's beyond me. Yeah, I have to confess. Yeah. Mathematics is a huge field. We kind of specialize, especially nowadays. There's very different branch. Even within pure mathematics, there are many subfields. Applied mathematics, many subfields. So what I'm talking about here more on the discrete side, and there's a PDE side. I have not used like level set image processing. There's a lot of it becomes very specialized, and there's a statistic probability, and no, this is a huge field. Yeah. Right. There's a question here. Okay, good. If you can answer that. Ah, okay, that's great. Yeah. Huh?
Considering computational mathematics as my major, can you tell me a little bit more about this field? Is it all encompassing like what you showed us today, like encompass all these fields of math, all these fields of biology and all that?
No, I would say that as a major in computational mathematics, in fact, our undergraduate students ask the same question, right? What do they need to learn to really qualify, to well prepare? Because the field is so huge. And I think that what we can teach you, teach our students, including students in PCC, is some basic fundamental theory, like you have to know calculus, you have to know numerical, you have to know linear algebra, some analysis, differential equation, right? Some probability theory. And then based on that, you have to make some connection to application, right? You have to learn some scientific field, like a physicist, could be engineer, it could be imaging, could be control. So we also require students to take a lot of outside elective, right? So it is a combination of these two, and the application I show you, it comes later in the graduate school or when you go to work, right? It's not like you learn something in the year 1 or year 2, like in PCC, you're ready to do this. No, it's not that fast. So that's why a lot of people are impatient. They do not quite see the fruit, right? If I work hard here, what is it going to be useful for? I cannot wait. I'm eager to get a job right away, get a reward right away. If you don't have the patience, you don't get the fruit. I think the point is that you need to invest in the time. And the good thing about it is that many companies recognize it's important. So they like to recruit people who have the mathematical training, the background, who programming skill, abstraction technique, who understand physics, and then you're much more marketable if you have that. But of course, we have a well set of curriculum, right? You go through this basic, everybody required to take this set of courses. There's some elective. You can depend on personal interest because it's such a vast field, right? Different application to biology, to image, to material science, to finance, to a huge set of, but you cannot do everything, right? Here, just to show you, highlight a few examples, mathematics could be relevant, right? Has been proven to be useful, yeah. But you cannot, as a major, your time is too short, right? If you do what I show you, today is not meant to show you what mathematical major, a computation major is supposed to be look like, because then you're not going to learn anything deep at the end. I think you have to learn a few things solid, and then realize how they can be applied for applied mathematics department compared to a pure math department. They much more emphasize on just the pure abstract theory. They don't, even throughout the 4 years, you don't need to see any application. That's fine for them. But for us, it's different. Yeah. We want to show there's a connection there. Yeah. How do you get used? Yeah, I think patience it is rewarding. Nowadays, people don't have much patience, but the patience is rewarding. Yeah.
Well, for math, like learning is patient, but for my students, because they take algebra 2 now,
Yeah.
so how is the way, does someone interest them to learn more?
Well, that's the main one of the purpose I want to convey. I don't know if it's successful enough, that if you learn enough, because we are doing a building block, you're building the foundation right now, right? You cannot tell them that, well, if you come out of PCC, you take a 2 or 3 set of math courses, you talk about algebra, right? It's very low level math, right? So you cannot say that I promise you take these 3 set of courses, you will be going to be hired by Google or by Microsoft, or you make a huge money. No, you cannot do. You cannot promise them that. This is necessary preparation, right? And then you go to the next step. Then you can do more fun stuff, right? Then you are more ready, right? So you should tell them there's a path leading to that, right? But this is the step. You have to do step by step. You have to build a foundation, like people doing practice martial art in Shaolin martial art. The first few years they're doing very boring routine stuff, right? They just doing this, right? They do a lot of work, but that is building their body ready to take those techniques. It takes a long time to do that. Not like a day one that teach you a few techniques. It's good for show, but you cannot really fight, right? I think you need to just convey that it is an investment for the future, but only if you have the passion in it. We shouldn't convince people that who are not interested, have no talent or interest in mathematics. If you can only inspire the student who has a passion, they're good, has a talent, and then don't give up on it because of short-term interest, right? Think about if you keep investing, if you're really good at it, then you have a bright future. My teacher inspired me that way when I was at UCLA. Many of my classmates will switch major to WE, computer science, because they thought it's easy to find a job. At that time, the Wall Street Journal did not rank mathematician as the best employable job. No, people think mathematics will be a high school teacher or college teacher. It's very hard to find a job. But I met a very good teacher at UCLA. He said, don't worry about it. Do your best. If that's what you're good at, go all the way to the top. Then you'll be useful. People will hire you. And that's what I did. We talk about how mathematics benefit the quality of our life. I think mathematics the quality of my own life tremendously. I love to do what I do, get very well paid, and I really cannot be more grateful. Yeah, but it is a long-term investment. And it's better if you really have a passion, because then you really enjoy it, and then you can really deliver good result, right? And even if you do not choose mathematics as your own career, as I say, that there's a lot of other revenue that you can make an impact. Yeah. At least for those people who work with me as a student or as a postdoc, they proven to be very useful in the industry. I was very proud of them, and they really proved themselves. Change the image to their boss. For many years, those people only hire chemical engineer or mechanical engineer or civil engineer in the oil industry or in the and now they see how the mathematician function, how do they can make a breakthrough, completely eye-opening for them, for their management people. Yeah. So maybe it's a time to stop, almost 6 o'clock. I was told that we're supposed to end at 6 o'clock. So but thank you so much for participating. I really enjoyed it.
Thank you very much, Dr. Hao, and thank everyone here. And I hope that you enjoy his talk. And we would like to say that we hope to see you all next year. And remember next year that the raffle ticket, you will print your name clearly.
Maybe put down an email address or a phone number.
Yeah.
Yeah.
Okay, so now it's already 6 o'clock. Any more questions? Or if you have any suggestions or you have any feedback about this event, welcome to send your feedback or suggestions to the following email address, which is pcc.pi.day@gmail.com. Okay? All right. Thank you so much.